Chapter 6, questions 28 and 29 are asking about intermolecular forces. And to understand those, we have to start with electronegativity. Remember that electronegativity is how strongly a nucleus attracts valence electrons. Now so the nucleus, that's at the center of the atom where the protons and the neutrons are, and then electrons wrap around that nucleus in layers, sort of like layers in an onion. The outermost layer is crucial because that's the one that knocks into stuff in the world and determines whether the atom will stick to it or not. So it has a special name, it's called the valence layer, and the electrons in that layer are called valence electrons. Now, how much the nucleus has protons in it, the protons are positive, those electrons in that valence layer are negative, so they're going to be drawn to it. That attraction, and notice it's only from the nucleus to the valence electrons, that attraction is electronegativity. So electronegativity is how strong a nucleus attracts valence electrons. The trend for that we've seen is that elements become more electronegative as you go up and as you go right on the periodic table. Here's a periodic table that gives you numbers for how strong the electronegativity is. The larger the number, the stronger the electronegativity. In other words, the more the nucleus will attract those valence electrons. So in the top right, you have the most electronegative elements: nitrogen, oxygen, fluorine, and chlorine. Notice, if you were looking at the numbers, those would be the only elements on the periodic table that have numbers that are 3 or higher. So the nuclei in those atoms are really going to attract valence electrons. So that becomes significant because the valence electrons are the electrons that atoms share in bonds. And if you have these extremely electronegative elements, nitrogen, oxygen, fluorine, or chlorine, that are in a covalent bond, they're not going to share the electrons equally. So let's think about the case for water. In water, you have oxygen, that really electronegative element. So the lines here represent 2 electrons that are being shared. It's a covalent bond. But the electrons are not going to be shared equally because oxygen is so electronegative. So the electrons are going to be more attracted to the oxygen. The electrons are going to spend more time around that oxygen. And so the oxygen is going to be slightly, and the symbol for slightly is this lowercase Greek letter delta. It looks kind of like a squiggly D. It's going to be slightly negative. The hydrogens are losing those electrons. The electrons are more attracted to the oxygen because oxygen is more electronegative, so they move toward the oxygen and away from the hydrogens. If electrons are not around the hydrogens, the hydrogen is losing the negative charge that comes with the electrons. Losing negative charge will give the hydrogen a slightly positive charge. So each of these hydrogens would be slightly positive. And these slight charges, the slight negative charge on oxygen and the slight positive charges on hydrogen, are coming from differences in electronegativity. Electronegativity is how much an atom attracts valence electrons. If you have one atom that is really electronegative, so it's really attracting valence electrons, and let's say these are sharing that one electron. So let's say you had like oxygen here on the left and then hydrogen on the right. So oxygen is really, really electronegative. They're sharing this electron there. Oxygen is really, really electronegative, so it is going to pull that electron towards it really hard. And hydrogen is not that electronegative, so it's not going to pull it that hard. So the electron is going to spend more time around the oxygen. And so the oxygen borrows some of the charge from the electron and becomes slightly negative. The hydrogen loses it, and so it becomes slightly positive. Okay. So, then we can go back down here, and that's how you get those partial charges on this water molecule. So that ends up creating that stickiness in that molecule. So when you get two of the water molecules together, you could see how the slight positive charge on the hydrogen will be attracted to the slight negative charge on the oxygen. That attraction between those charges is a hydrogen bond. It's really a misnomer. It's not a bond. That attraction is 30 times weaker than a covalent bond. But it is attracting them, it is a stickiness, and that stickiness is a hydrogen bond. Because the difference in electronegativity between oxygen and hydrogen is so big, these are almost full charges, and so this attraction is really strong because it's almost full charges. And that makes hydrogen bonding the strongest intermolecular force, because the partial positive and negative charges are so big. So they're almost full charges, and so the attraction between them is really, really strong. Compare that to what happens in a different sort of molecule. So if we go to this second one over here, you'll see that you have oxygen, which is still really electronegative. So it pulls the electrons to itself and becomes slightly negative. The carbons bonded to it lose those electrons when they go toward the oxygen, and so those become slightly positive. But the difference in electronegativity between oxygen and carbon is not as big as the difference between oxygen and hydrogen. So the charge is not as big. The charge on hydrogen here on the left is almost a full charge, but the charge on the carbon here is not a full charge. It's not even close. It'd be closer to maybe a half of a charge, because carbon is more electronegative than hydrogen, and so it is attracting the electrons a little bit back toward itself. So when you get two molecules like this together, there is still an attraction between the slightly negative oxygen on one of them and the slightly positive carbon on the other. That attraction is called a dipole-dipole interaction. And hopefully that would make sense. This here is a bond that has two ends, a negative end and a positive end. And the way you say negative, the way you'd say two is di, and the way you'd say end is pole. For example, the North and South Pole are opposite ends of the Earth. So that's one dipole, and that's interacting with another dipole, a bond that has two ends, a positive and negative end, in another molecule. So because it's an interaction between two dipoles, it's called a dipole-dipole interaction. So those are two intermolecular forces. Because they're making two molecules stick together, intermolecular. But hydrogen bonding is the strongest, and then dipole-dipole would be the next. The weakest is called London dispersion forces. And these happen in every molecule all the time. They are not the result of differences in electronegativity. Instead, imagine that you have two atoms here, and let's just think about the atom on the left. There's no guarantee that electrons are going to be evenly spaced around an atom at any given time. They're flying around randomly like gnats in a cloud. And so, for a fraction of a second, all the electrons could be on just one side of the atom. And for that fraction of a second, that side, actually let me do this in purple, for that fraction of a second, that side would be slightly negative. And the other side, where they're missing, would be slightly positive. Now, if that same thing happens to another atom that's right next door to it, then that side of that atom would also be slightly negative, and the other side would be slightly positive. And the positive side on one would be attracted to the negative side of the other atom, and that attraction would be a London dispersion force. In anatomy and physiology textbooks, you may see that called a van der Waals interaction. Now, you might even say, that sounds so, like if the electrons are moving around over 2,000 miles per hour in each atom, so they move so fast, how long would this exist? Is it even significant? But remember the different time scale that atoms exist on. 1 second to us is like 219,000 years to an atom. So if the electrons arrange themselves like this, on two atoms next to each other, only, say, the equivalent of once every 500 years, over the course of 1 second, 219,000 years, it would happen many times, and we would see an aggregate stickiness between the two atoms. So that's a London dispersion force. It's the weakest intermolecular force of the three. So these are the three hydrogen bonding dipole-dipole interactions in London dispersion forces, from strongest to weakest. They're ways that different molecules can stick to each other. They're different from bonds because they're much weaker on the whole. Now, in these questions, they're asking you to identify the strongest attractive force, the strongest intermolecular force between molecules. And we're going to make a big assumption. We're going to make the assumption that the dipoles in a molecule will not cancel each other out. I'll mention this again after we walk through this flowchart, but so long as we make that assumption, this flowchart will be valid. Okay, so the first thing you'll want to do is to ask yourself, is there a nitrogen, oxygen, fluorine, or chlorine in the molecule? If there is, then you have these really electronegative elements that can cause hydrogen bonding or dipole-dipole interactions. So if there is, then it's either hydrogen bonding or dipole-dipole. If there is not, then you can't create a dipole, and the only intermolecular force that's left is London dispersion forces. That's the only one that doesn't need to have very electronegative atoms. That's everywhere all the time. Okay, so if there is a nitrogen, oxygen, fluorine, or chlorine, then you have to ask yourself another question. Is that nitrogen, oxygen, fluorine, or chlorine bonded directly to a hydrogen? If it is, like in the case of water, you can see the oxygen is bonded directly to hydrogen, then you'll have that hydrogen bonding. The difference in electronegativity will be so big that the positive charge on hydrogen and the negative charge on oxygen will be almost full, and they'll really attract each other in a strong way. If there's not, if the nitrogen, oxygen, or fluorine is bonded to another element, let's say carbon, then the charges won't be as big, and they will only stick together as dipole-dipole interactions. So this is the flowchart that you can use to decide which intermolecular force is going to stick these molecules together. So armed with this framework, let's analyze a few of these problems, this conceptual framework. So let's look at this first one. It's CH3OH. Now first, is there a nitrogen, oxygen, fluorine, or chlorine in the molecule? There is an oxygen right there. Okay, so now we're at this question. Is the nitrogen, oxygen, fluorine, or chlorine bonded to hydrogen? And we can see that it is. So, between molecules of these, the strongest intermolecular force would be hydrogen bonding. Okay, next, this second molecule, CO, carbon monoxide. First question we'd ask ourselves, is there a nitrogen, oxygen, fluorine, or chlorine in the molecule? And there is. It's right here. Okay, so we're going yes. Next question, is the nitrogen, oxygen, fluorine, or chlorine bonded to hydrogen? And we see that it's not. So the strongest intermolecular force that could exist here are dipole-dipole interactions. So that's what we would want to include For the third one, CF4, first, is there a nitrogen, oxygen, fluorine, or chlorine in the molecule? And we see fluorine. So we'd go to yes. The next question is the nitrogen, oxygen, fluorine, or chlorine bonded to a hydrogen? And we don't see a hydrogen here. So the strongest intermolecular force that we would have in this one, according to this flow chart, would be dipole-dipole interactions. Oops. Now, this is a good opportunity to discuss that assumption that we were making before. The assumption we're making is that a dipole, the dipoles on the molecules won't cancel each other out. Let's look at this molecule for a second. Remember that one way you could draw dipoles is to draw the slightly negative, the delta minus, and the delta plus on the two atoms in the bond. The slightly negative goes over the electronegative element. But another way that you can express that same concept is to draw an arrow pointing in the direction of the negative sign with a positive sign at the tail, where the positive sign would be. And that arrow is telling you where the electrons would go. Now, fluorine is more electronegative than carbon, so in each of these bonds, you would have a dipole that points toward the fluorine. So each of these bonds would give rise to dipole-dipole interactions with another molecule, except the one that goes up cancels out with the one that goes down. They're pulling in opposite directions and they end up canceling each other out. The one that goes left cancels out with the one that goes right. They're pulling in opposite directions and so they cancel each other out. So technically, that destroys the dipole in this molecule, and it wouldn't be able to create dipole-dipole interactions because the dipoles in each molecule are destroyed. Technically, the correct answer for this one would be London dispersion forces. However, on my particular exams for this course, Principles of Chemistry, you will not have to worry about dipoles canceling out like this. And so, you can just follow this flowchart as is. The assumption is that the dipoles don't cancel out when you use this flowchart. I'm going to leave this dipole-dipole interactions here because that's how you would answer the question on an exam. But just keep in mind, if the dipoles ever cancel each other out, say for example if they had a question like this on the Hesse, you would want to check to see if the dipoles cancel out, and then adjust your answer if they do. Alright, let's try this bottom one. CH3CH3. First question, is there a nitrogen, oxygen, or fluorine or chlorine in the molecule? And there's not. And so the strongest intermolecular force here will be London dispersion forces. Okay, so that's how we could figure out how sticky these molecules are going to be to each other. These CH3OH molecules are going to be really sticky to each other. The CO, the carbon monoxide, won't be as sticky, but will still kind of stick to each other because they have the next strongest intermolecular force. And these at the bottom will barely stick together at all because they're only held together by London dispersion forces. Knowing that will help you determine whether a substance would either be a solid, liquid, or gas at a certain temperature. Okay, let's try that using that same flowchart with question 29. So first, we're making an assumption that the dipoles don't cancel out. Is there a nitrogen, oxygen, or fluorine or chlorine in this molecule? There is. So yes, we'll go to the next question. Is it bonded to a hydrogen? It's not. So using this flowchart, we would predict that these molecules would stick together through dipole-dipole interactions. So if this were a test question, that would be what the answer would be on my exam. However, I would not give this particular molecule on a test question because on this, you would have to think outside of this flowchart. Remember that the dipoles arise from differences in electronegativity. But which atom is more electronegative, oxygen or oxygen? Neither. They have the same electronegativity, they're the same element. And so there would not be any separation of charge. There's no reason for one to be negative or one to be positive. They attract electrons equally, so you would not have dipoles in this. And technically, the correct answer for this question would be London dispersion forces. However, to be consistent with the way that you would solve the question on the exam, I'm going to leave dipole-dipole interactions on here. Remember that on my exam, I will only give molecules where this flowchart is valid. I'm pointing out these other exceptions in the homework because you may see them on a Hesse exam. Okay, let's try this next one. SiH4. First question, is there a nitrogen, oxygen, fluorine, or chlorine in the molecule? There's not. So, this must be sticking together through London dispersion forces. So that's how these molecules will stick to each other. All right, let's go to C. Is there a nitrogen, oxygen, fluorine, or chlorine in this molecule? There is. So we'll go down to this next question. Is the nitrogen, oxygen, fluorine, or chlorine bonded to a hydrogen? Now this is kind of tricky because it is written next to a hydrogen. But if you were to draw the Lewis dot structures of each of these atoms, you would see that carbon has the 4 dots, each hydrogen would have 1 dot, and the chlorine would have 7 dots. And the only way all of these can fit together is if the hydrogens each attach to the carbon and the chlorine attaches to the carbon. If the chlorine only has 1 unpaired electron, and so it can only form 1 bond. So if it made a bond to the hydrogens, then it wouldn't be able to connect to the rest of the molecule. So technically, in this example, the chlorine is not bonded to the hydrogen. And so the strongest thing sticking this together would be dipole-dipole interactions. So we'll take that, and that would be, that would be the strongest intermolecular force for this molecule. Okay, last but not least, let's think about H2O2, hydrogen peroxide. So, first question, is there a nitrogen, oxygen, fluorine, or chlorine in the molecule? There is. Second, so we'll go down to the right. Next question, is the nitrogen, oxygen, fluorine, or chlorine bonded to hydrogen? And we see that it is. And so, we'll go to the right again. The strongest intermolecular force here that will make the molecules stick together will be hydrogen bonding. Okay, so what you should take away from these questions is that differences in electronegativity give rise to partial charges. Those partial charges make molecules stick together, stick to each other, either very strongly or weakly. That stickiness determines whether things are solids, liquids, or gases at different temperatures. And provided that none of the dipoles cancel each other out, you can follow this flowchart. Certainly on my exam, you can follow this flowchart to figure out which intermolecular force is making molecules stick together when they're all in a group in a container.